Hello. Game playing is one of the less boring aspects of artificial intelligence and is, in principle at least, fairly easy to understand. Now I should point out that the sort of games I'm talking about aren't video games. We're not concerned with Gears of War or Fortnite here. No, these are the sort of games played between two opponents, with each making a move, followed by his opponent, and so on. It's chess, draughts, backgammon, and so on. Also, the theory becomes useless if there is any random element involved. So we're not talking about games like Monopoly or Snakes and Ladders. We have our two-player game, governed only by logic, with a human as one of the players and a computer as the other. The first thing we need to do is to turn any board position into a number, to give a score to any board position. I'll be terribly conventional here and use chess as the example. Now, don't expect me to explain the rules of chess. I assume you already know how to play chess, even if, like me, you aren't very good at it. The obvious way to score a chess game in mid-play will be to give each chess piece on the board a basic value. Some pieces are more powerful than others, so they have different basic scores. A lowly pawn, for example, might be worth 1 point, while a queen, much more powerful, might be worth 8 points. The king has a very high score, typically 100 or 1,000 or something similar, since it is the one piece that if it is captured, the game is lost. The whole idea of chess is to put the king in a position where he can't escape, checkmate, and his high score reflects this. However, it isn't enough just to tot up the basic scores of the pieces on the board, as that doesn't take into account that those pieces can be placed strategically around the board. Looking at this example shows that the white queen is much more free to move around the board than the black queen, which is totally hemmed in, and threatens 3 enemy pieces at the same time. This should be taken into account when scoring any board position. Of course, there are 2 sides in the chess game, white and black. The convention is that the final score for the board is found by subtracting the score for the black side from the score for the white side. A high score on the positive side, such as 120, indicates a board position that is good for white. A low score on the negative side, low in the sense of large in magnitude, e.g. minus 120, indicates a score that is good for black. Let's assume that it's the computer's turn, and at this stage of play it can make one of 3 moves. If it's a chess game, we'll say for convenience it only has 3 possible moves. It can move a bishop, a rook, or a knight. In practice, each side in a chess game typically has about 40 possible moves at any stage, although this decreases as the game enters its end stages. However, we'll stick to these 3 possible moves just to demonstrate the principle of the thing. The simple approach is to evaluate the board positions that would result from each of these 3 moves. Moving the bishop gives a board score of 12, moving the rook a board score of 19, and moving the knight a board score of 12 again. Assuming that the computer is playing white and wants to maximise the score, the strategy seems simple. Move the rook to increase the overall score as much as possible. But hold on there. Don't forget that the human player, playing black, then responds to that move. Again, we'll assume that the human is very restricted in his moves and can only move as shown, producing the scores shown. The human player will try to minimise the overall board score, as lower scores favour black. If the computer moves the bishop, the human will respond with a move that gives a board score of minus 10. If the computer moves the rook, the human responds with a move that gives a board score of minus 7. If the computer moves the knight, the human responds with a move that gives a board score of minus 11. This rewrites the situation completely. Now the best move, that is to say the least bad move, is to move the rook. We end up in a bad situation, but at least the score isn't any lower than minus 7. The computer moves the rook. One thing to note with this strategy is that it always assumes that the opponent will make the best possible move. A human chess player playing against a much inferior opponent might chance his arm and move the knight in the same situation, in the hope that his opponent wouldn't notice the good comeback. However, the computer using this approach always plays it safe, and assumes that it's playing against an opponent that will always make the best possible move at any stage. Incidentally, the fact that the algorithm always assumes that the opponent makes the best possible move gives a reason why we couldn't use this approach to play noughts and crosses. As anyone who's watched the film War Games will tell you, it's always possible to force a draw in that game. So if each player used the best strategy, all games would end in a draw. expanding all the branches as far as they could possibly go, and then copying the values back as appropriate, would result in each branch at the top level leading to a drawn game. As the computer concludes in the film, the only winning strategy is not to play. A practical chess playing program wouldn't stop at one move from each player. Let's add another set of branches to the tree, representing the computer's response to the human's response. We know that the computer will choose the best possible move given any particular board position, so we can copy up the highest value at each point that used to be a leaf node of the tree to represent the new board score for the human's move. Like that. Repeating the logic from before, we assume that the human picks the best move from the ones available, meaning that we should only copy the smallest value at this human level up to the level above. Now you can clearly see that this three-level model suggests moving the bishop, as it gives the highest board score taking the next two moves into account. A real chess-playing program wouldn't limit itself to looking 3 moves ahead. It would look as far forward as memory and processing speed would allow. No human opponent would appreciate the computer taking an hour to make a move, and some time limit would be imposed, further limiting how many levels of the tree could be accommodated. There is one other factor to take into account, and that's the horizon effect. Whichever level the computer stops at, there is always a possibility that a particularly good board position, or a particularly bad one, lies just out of view on the level below it, just over the horizon if you like. Well, the algorithm has to draw the line somewhere, so it's a risk that can't be avoided. This procedure is called Minimax, as we descend to the leaves of the tree at the bottom, evaluating board positions and copying either the minimum or the maximum values back up to the next level, alternating at every level. The program does not evaluate board positions at any stage in the middle of the tree, only at the leaf nodes. So in the situation shown, it would evaluate a total of 18 board positions. Even so, this process is very heavy on computing power, and game-playing programs have to be written in the lowest level code possible, in machine code really, to make them practical. The fact that only board positions representing leaf nodes are to be evaluated means that the program must know in advance how many levels are going to be needed, as it has to calculate board positions to the final level before it can evaluate anything. Some chess-playing computers are set up that if they find the optimum move given a certain number of levels with sufficient time to spare, they can then try another level even deeper down to see if it gives a better move. This is an incremental approach. Start by getting the best move for a smaller number of levels, store that best move, and then work on the best move for one more level. Store the best move at this stage, then work on the next level and so on. At some point, the computer will run out of time, in which case it always has a current best move available. This approach does mean that the computer has to store quite a lot of intermediate data, such as incomplete paths through the tree and board positions which don't correspond to leaf nodes, in order to avoid having to duplicate work getting down to the bottom level to have a go at the next layer. But it does mean that the program is never caught without a suitable move. However, there is one dodge that we can use to streamline the process slightly, and that's called alpha-beta. We use it to prune the number of branches and reduce the workload quite considerably. We define 2 variables representing 2 different limits. The first is called alpha, and it represents the best possible score that a maximizing level can guarantee at any particular node or below meaning towards the leaves. It starts with a dummy value of -infinity and is increased as the tree is traversed. As soon as a better score than -infinity is found, alpha becomes that new value. And if a better score than that is found again, alpha is updated to that new score, and so on. Alpha only ever increases. In practice, infinity will be represented by a very high value, such as 1,000,000, so the initial value of alpha will be -1,000,000. The other variable is beta, and it works in exactly the same way, except that it only applies to minimizing levels. As such, beta starts off at a value of +infinity, or in practice +1,000,000. Whenever a score is found on a minimizing level that is lower than beta, beta is reduced to that score. Think of alpha and beta as being like a high watermark and a low watermark, with alpha only applying to maximizing levels and beta only applying to minimizing ones. The tree is traversed as before, but each node that isn't a leaf is compared to either alpha or beta as appropriate. If the best possible score that we've worked out so far at that node is worse than alpha or beta, then the algorithm gives up on that node and doesn't bother to work out anything else from it. It can't contain a score that will be passed back up the tree, so why waste time evaluating it anymore? This is all very abstract, so I shall illustrate it with an example. In fact, I've yet to see alpha-beta pruning laid out in the series of algorithmic rules. It's only ever explained in terms of examples, so I'll do the same thing. Take a look at this very simple tree. I've labelled the nodes from 1 to 7, and the computer wants to maximise the score. So the branch corresponding to the highest guaranteed score will be chosen. Firstly, the computer goes down the left side of the tree and evaluates the leaf position that it comes across. This is a maximising level, so the value of -3 is compared to alpha, currently -1,000,000. -3 is better than that, as indeed would any ball position be. So alpha now becomes -3 as shown. Then the board position next to that one is evaluated, giving 5. This is compared to alpha and is bigger than it, so alpha becomes 5. The minimizing level now compares the value of 5 at node 4 to beta, choosing the smaller one. Beta is still +infinity, so the value of 5 wins, and this becomes the new value of beta at node 2. The minimizing level is now guaranteed a score of at least 5, even if all the scores on the right side of the tree are worse. Now the computer checks the other half of that branch. At node 5, we evaluate the first node and compare it to a value of -infinity. I know what you're thinking. Wasn't alpha updated to 5? Well, that was for node 4. This is a new alpha for node 5. Anyway, the first ball position evaluated at node 5 gives a score of 7. This is the new value of alpha at node 5. Moving up to the minimizing level, the value of beta is 5, which is compared to the new value of 7 on the other branch. No dice, I'm afraid. The minimizing level will only update beta if a value is found less than 5, which 7 isn't. This means that the entire sub-branch corresponding to node 5 can be pruned away. That means the fourth ball position, the one that would have scored 11, is never evaluated. We have saved the work of evaluating one board position so far. But, I hear you say, that 11 would have been a marvellous score. In fact, it's the highest leaf value there is. Yes, I hear myself reply, and that value would have trumped the 7 and become the new value of alpha at node 5. But that's as far as it would have got. The minimizing level, being the pessimist that it is, would have compared the 11 with 5 and chosen the 5 instead, since the human opponent would never have allowed the computer to get to that board position. Remember, the human always plays the best strategy at any point, and on that left branch, the best score the human can hope for is 5. Not -3, because the computer in turn will prevent that happening. OK, you counter? What if that value of 11 had been a really low value, like -30? That's definitely lower than the value of beta at the minimizing level. We never got to work it out, so the computer would never know. True, but if that had been the case, it would never have made its way up even one level. The maximizing level would have compared the -30 with the +7 and chosen the +7 instead. Whatever that score had been, it would have been blocked, either at node 5, if it had been less than 7, or at node 2, if it had been more than 5. The value of beta at node 2 is passed up to node 1. That is a maximizing level, so node 1 compares the score of 5 with its own value of alpha, -infinity, and changes its own value of alpha to 5. Now the computer tackles the other branch, going left at every turn until it reaches the ball position with a score of -8. It compares it to the value of alpha at node 6, which has been reset to -infinity for that node. -8 is larger than -infinity, so the new value of alpha at that node is -8. This value is passed up the tree to the minimizing level, which compares it with the values of beta at node 3. This is the dummy value of +infinity. No, not 5. That's the value of beta at node 2. -8 is less than +infinity, so the minimizing level chooses -8 to be the new value of beta at that node. Now the top node, node 1, has two values to compare. It's guaranteed a score of 5 from the left-hand branch. Node 3, being part of a minimizing level, cannot produce a score better than -8, whatever happens on that rightmost sub-branch. The value of beta at that node is -8 and cannot rise above that. This means that the final choice of move is to go for the 5 score. The computer makes the move corresponding to node 2. In the final analysis, we only had to evaluate 3 of the 8 final board positions. Either of the 2 scores at node 7 would have beaten the -8 at node 3 in the minimizing level, just as the score of -4 would have beaten -8 at the maximizing level. But we never needed to evaluate any of those, as they wouldn't have affected the final outcome. Granted, this example was rather contrived to demonstrate a high degree of pruning, but in general, alpha-beta does indeed drastically reduce the workload of the game-playing computer. So there you have it. As far as I know, all computer programs that play competitive games use the Minimax algorithm with alpha-beta pruning. Of course, there might be some new method in use, perhaps using neural networks, but if there is, I don't know about it. The approach that you see here has been working perfectly well since the beginning days of artificial intelligence, and, as a result, has become universal. The next video I upload will be a JavaScript program showing Minimax in action, and after that we shall move to another topic. I haven't quite decided what yet, so watch this space. In fact, it might be a good idea if you clicked on that subscribe button so that you will be the first of my viewers to find out. Don't forget to click on the bell icon to make sure. Please also click on the like button, and of course, I would welcome a comment below. Thank you.